please help me extend a warm skyscraper welcome to Anthony Wagner, Nick Wagner.
Hey everyone, I'm Nick Wagner. I'm a postdoctoral researcher over at Brown. I've been here for about a year. Actually, in about 2 weeks, it'll be about a year since I've moved up to Rhode Island after previously have never lived close to New England. So it's been a fun year. Good weather, good food, good people. But today I'm going to be giving a talk sort of broadly about both what I do but also what the planetary science community, the scientific community, understands about the interior state of the moon, both compositionally, thermally, but also how both of those properties change through time, so the temporal evolution of it. A little background on me, I already spoiled the fact that I'm not from New England. I actually got my start down in North Georgia. I was born about 40 minutes from the start of the Appalachian Trail. So similar geology, just the southern tip of it. I then went off and studied geophysics at the Colorado School of Mines, gallivanting amongst granites and tilted sandstones and other really cool geologic outcrops. And you can probably already tell my training isn't in astronomy. I kind of started on Earth and then leapt out at one point. But Mines has a in situ resource utilization program that started when I was there, thinking about how to harness usable materials on other bodies such as the moon or asteroids. And they're pushing forward mining helium-3 and ice in some of the permanently shattered regions of the south pole of the moon. So they're doing cool stuff. But I went a different direction. I got really enamored by geophysical methods such as like seismology, gravitational methods, electromagnetic methods to actually like give us a picture of what's inside both the Earth, but other planets. And then from Colorado, I moved on down to Waco, Texas to do my PhD at Baylor University. And this was my PhD's advisor's little mascot. It's like the retro Baylor bear with a astronaut helmet on it. It's pretty cute. But I did my PhD mainly on studying Mars. The moon is actually kind of newish to me in a way. But I studied how we can use measurements of variations in the gravity field to image about the top 100 kilometers of the crust of Mars and think about future NASA mission opportunities to do good science on Mars. But like I said, about a year ago, I defended my PhD, and then I went all the way up to Rhode Island. I work with Harriet Lau now, sort of championing and developing a technique called tidal tomography, where kind of like a CAT scan, you can image the interior of not a person's body, but a planetary body. And I use tides to do that. Another common imaging technique is seismic tomography. That's used a lot on Earth. But we don't have a lot of good seismic data on the moon or other planets. But we do have really good accessible tidal data. So I think I spoiled a little bit of this, but the broad outline of the talk that I'll give tonight, we'll start way back 4-ish billion years ago for the focusing on the formation of the moon, some information onto how do we know this, and also maybe more importantly, why do we care? I'll then go into some of the methods and data that we, meaning me and other geophysicists, use to study the interior of the moon. But these methods and data are pretty applicable to other planetary bodies as well. Third, which I think is probably on everyone's mind tonight, is how do we know the moon isn't made of cheese? And there's a really interesting paper from 1970 that actually goes in first principles of measurements of the material properties of different kinds of cheeses and some of the Apollo samples, and does like a 1-to-1 comparison. It's kind of fun. And then tying this all up, hopefully in a nice little bow, how does everything I just blabbed about relate to some of the research I conduct at Brown? So yeah, and without further ado, I'm going to jump right in. For those unfamiliar, the moon was likely to have formed in a giant impact, again, 4-ish billion years ago. Oh, that's kind of choppy. That's sad. it gets the point across. This is a hydrocode simulation of the proto-Earth and an object called Theia smashing into each other, creating this large disk of material and debris. And eventually that cloud coalesces into the moon. And then eventually, all right, it's restarting again, but the moon, or sorry, not the moon, the Earth forms afterwards. And yeah, it's mentioning here the object that struck Earth. It's called Theia. It's about, we think it's about the size of Mars based on the total mass of the moon, the Earth, and then the total angular momentum of the system. Additionally, this is the what I'll call like the canonical model. There's another one where this model doesn't actually match some of the isotopic compositions we measure from Apollo measurements. So there's another model that it's a really high energy impact of this that creates what's called a synestia. That's just there you can see little blobs and liquid that's sort of going around. In a synestia, it's completely vaporized essentially. But the issue with that model is it doesn't completely conserve the angular momentum of the system. So there's actually active research being conducted on the Earth-Moon formation. Immediately after this really energetic collision, it's likely that the moon was completely liquid, or at least most liquid, bearing probably a solid iron core. What happens immediately after that happens is you have a crust that forms on the surface of the moon, and an orthosite-rich crust, which actually last weekend I went camping near the Adirondacks, near about 2 hours north of Herkimer. And there's a nice little outcrop of anorthosite that formed about 1 billion years ago that's really similar in composition to the anorthosite crust that floats out of this magma ocean. So in this magma ocean, the bulk chemistry of the liquid starts crystallizing out different minerals. The first of which is anorthosite. It's lighter, so it goes to the surface. Oh, I forgot to mention, the first one is actually olivine. It's very dense, so it crystallizes out in the liquid and falls down to the bottom. I guess it's a little bit later, you actually have the anorthosite start to float up to the top. And as you keep crystallizing out this magma ocean, what you're left with is called, a lot of people call it creep, which stands for potassium rare earth element, phosphorus rich titanium oxide stuff mainly. Essentially, it's whatever's incompatible into some of the mineral assemblages that are crystallizing out of the magma ocean sequence. So likely within 100, 200 million-ish years, the moon is going to look broadly like this. And this is where it gets complicated and people start arguing about things. So I mentioned creep. It's important because there's a lot of radioactive elements in it, so it keeps it warm. On the near side of the moon, on the top left figure, and if we stepped outside and actually looked at the moon, you see this dark splotch on the near side. Those are Mare basalts, and they are not part of this diagram I was showing before because it's secondary magmatism. But you need some sort of source to generate that magma, separate out the basalt from the secondary melted crust and actually erupt it out onto the surface. Some ideas to do that are related to what's called magma ocean overturn. Those last dregs I mentioned in this slide, they're gravitationally unstable, which means that the crystals that eventually form here are denser than the underlying material. So they want to start to sink. This is actually, I got this from a preprint earlier today, so it's not even published yet, but it's at least sent out into archive land, where you can get these diapirs of these denser materials sort of being sucked down towards the core mantle boundary. And that can provide enough heat to eventually generate some of the magma conduits that generated the Mare basalts a couple 100 million years later. You can see in the bottom left image, I realize that text is really small, but I'll walk through it. It's essentially measurements of thorium, which is another radioactive element. And you can see it lights up pretty much coincidentally with the Mare basalts on the near side. So it's pretty radioactive, relatively speaking. I think astronauts were okay from it. I think they had to worry more about solar wind and stuff. But this geologically distinct unit is kind of a puzzle piece in trying to figure out what happened after the magma ocean formed. So yeah, one thing I'm going to get into now is sort of like, how do we know some of this? What I've plotted on the right here, and again, just ignore the color bars for now, but it's the static gravity field of the moon. So gravity isn't constant across any body. Any variation in the density of materials within inside the Earth, the moon, Mars, etc., induce gravitational changes. And spacecraft actually feel these. There's slight changes in the velocity of the spacecraft as it orbits a planet. And some really creative engineers, kind of black boxy to me, but they can back out what this gravitational field is based on how the velocity of the spacecraft changes over time. But you can see broadly, there's a lot of splotches on here, really high gravity splotches. And that's actually where the mantle has come up into the crust, high density crust or high density mantle into the crust from really large impacts. Oh, I'm going to mess up the names because I don't know craters super well. But broadly, I think that's Crisium, Oriental, Tranquillitatis. Someone in here probably knows better than me. But these are 100-kilometer in diameter impacts that are so energetic that they end up uplifting the mantle beneath it. And actually, if I go here, you don't, besides the Mare basalts, you don't really see any surface image, any superficial distinctions that this was happening on the subsurface. So gravity is a really neat way to infer a lot of these properties about the interior of a planet. The next, which is probably more important, is, oh, I forgot. I have a nice little animation next. The spacecraft that actually reconstructed this gravity field, it's called GRAIL, Gravity Recovery and Interior Laboratory. It was launched in 2011, I think, and only orbited the moon for about 6 months. But this is sort of the latest and greatest gravity field. You can see how high resolution it is. But the way it works is I'm mentioning that you can measure changes in the velocity of a spacecraft, which means you need like a link to it. So Earth is looking at the spacecraft and sending data about its speed and velocity. What you can do that's a little bit higher precision is actually send 2 spacecrafts in tandem, kind of like this. This isn't GRAIL, but this is what GRAIL was based on. These are a spacecraft pair called GRACE, Gravity Recovery and Climate Observatory, I think. And there's actually some really nice names to these. I think the GRACE spacecraft were called Tom and Jerry. And then in GRAIL, it was called Ebb and Flow. I like Tom and Jerry a little bit better, but here's sort of the principle at work. As you're going over areas of higher density or higher topography, the leading spacecraft sort of speeds up. So if you can measure that distance really, really, really precisely, you can back out the gravity field. And I think, yep. So these are time variable, I think monthly estimates of Earth's gravity field over time. You can see the changes in the Amazon basin. A lot of this is climately controlled. The Himalayas, I'm trying to pick out anything else. But yeah, a lot of the signal isn't actually from the solid Earth body. It's from changes in the atmosphere, changes in the seasons, etc. In fact, it's so good that we actually have a monthly time series of how the Greenland ice sheet and Antarctic ice sheet have lost mass over time. So this is a moving video. You can see from about 2002 to when, I think GRACE is actually still going on, but there's a gap in data. There's GRACE and GRACE follow on. You can see over time, these little small wiggles are the yearly signal, but this overall large trend across 2 decades signifies about, yeah, almost 200 gigatons a year for Antarctica and almost 300 for Greenland. So this is a really sensitive tool that we've used to great effect on Earth, but on not Mars, on the moon, we're actually able to really precisely measure changes in the gravity field from tidal interactions from the Earth and Sun. And I'll get back. Yeah, I think I already said that. This is a representation of GRAIL communicating back to Earth, and it similarly to GRACE measures the distance as it's orbiting across. Actually, I don't know how fun the fact this is. I think it's fun. We will probably never get a better gravity field than we did with Grail, because the moon doesn't have an atmosphere, so you can get really close down to the surface, and gravity falls off as the inverse square of radius. So the closer you are to a planet, the better resolution your gravity field is. Earth, you can't do that. There's an atmosphere in the way, so there's too much drag and complicates things. So an airless body like the moon, it's perfect. You can actually get the in the animation I showed earlier, you can see like the spatial wavelength of those like blobs. The in the lunar gravity field, those blobs end up being like a kilometer size instead of a couple hundred kilometers like on Earth.
Can you take a question?
Yeah, always.
Go ahead, Laura.
Well, it's a comment. That system of two things has been used to map aquifers.
Yes.
On
Mhm.
Earth.
Yeah, definitely. Yeah, I know it's been used a lot in the Sierras in California to do that. And yeah, in that video, I was trying to point out the Amazon rainforest because there's just a large high and a large low as the monsoon season goes across. But it's been a really great marker of how water has transported across the Earth. Yeah, I already talked about the did I say mass gone? The mass concentration of that mantle coming in underneath. This is the Oriental impact basin, and there's generally this large red high, I'll call, in the middle. But this actually points out a really neat structure of some of these really large impact basins in that there's multiple rings. As the transient cavity of the moon sort of is forming, it's so large that some of the sides sort of slough down and create inner rings. And this is sort of a moat in blue, but this is sort of the inner ring of Oriental here. Yeah, I just like showing off Grail gravity a lot because I think it's neat. But you can see again spatially how sort of this is correlating with the topography of the moon. So just um, the vertical height of craters, the highlands, etc., on the moon. And again, you can kind of see like these impact basins here are nicely correlated with some of the high gravity signals from the mantle here, and here. But moving to seismology, the Apollo missions put 4 seismometers on the near side of the moon in the Mare. Generally, you can think of a seismic source from a earthquake, or in this case, a moonquake, as 2 sources: a P wave, where the energy is going in the same direction as the propagation, and an S wave, which on Earth end up causing a lot of the damage most of the time, where the wave is actually, if the wave is traveling this way, it's going perpendicular. But from measurements in that data, we were able to broadly figure out the large scale structure of the moon. And one interesting thing about it is that they're really spatially biased. So if this figure is a cross section of the moon, that's the near side, this is the far side. We only see really deep moonquakes. How deep is that? Probably 700, 800 kilometers deep on the near side, and it's quiet on the far side. And we still have no idea why that is. We don't know if that's a inherent property about moonquakes, or one thing I was showing here is that there's actually shadow zones where if a moonquake happens sort of on this far side, this red star up here isn't going to be able to see it because of properties of the liquid aquifer. There's actually a mission hopefully going to be launched next year called the Farsight Seismic Sweep. It's a I've been told it was a flight spare from the InSight seismometer, if y'all are familiar. But hopefully it'll be launched next year, and it's going to land here-ish, somewhere, I think somewhere in the South Powhatan Basin. But hopefully we'll actually get confirmation whether or not the far side, deep interior, is quiet or not. I'm actually going to skip this one because it's a lot going on and the screen is kind of small. But generally, from all these different models from seismology, we know the broad scale structure of the interior: crust, mantle, at least a liquid outer core, maybe a solid inner core, but I could talk about that for a while, so I'm going to move on. But more interestingly, especially to what I do, is geodesy. So changes in the gravity and shape of a planetary body. This little guy right here is essentially just a mirror. It's a retroreflector, more technically. But what I think, yeah, this was Apollo 11, but in the subsequent Apollo missions, a couple more were laid down. And essentially from Earth, you just range it. You send a pulse and you measure how long it takes to go back, and you can figure out how the surface has changed over time. Librations is just how the moon has kind of wiggled over time. If you were to look at the moon, the full moon for like 2 years, you're actually seeing more than 50% of the surface area because it's slightly wobbling. So you kind of see edges on the other side that equate to more than 50%. But the magnitude and direction of those are directly tied to the broad scale interior structure of the moon. So tides in general, I mentioned geodesy a lot just then. Generally speaking, it's tidal forces that are changing the surface height and that static gravity field I was mentioning earlier. And they're directly tied to the density and then the elastic properties of the interior of any body. But you can see here a nice little cartoon of the Earth on the left, the moon on the right, how the gravitational force sort of squishes it out in the direction of the moon from the gravitational attraction. And then because the Earth actually rotates faster than the moon does, the Earth rotates through the tidal bulge induced by the moon. And that's actually how you can get interesting spring and neap tides over time as they combine with or cancel out with the solar tide over time. A fun little tangent about tides, though, is that if we look at the rest of the solar system, they're kind of actually weak in the Earth-Moon system. The most exciting example of tidal interactions is in the Jovian system, so in Jupiter. The 4 largest moons, of which the Galilean satellites, Io, Europa, Ganymede, and Callisto, are in resonance with each other. So it ends up tugging and pulling and stretching Io a lot more than the moon does around Earth. And its orbit is slightly more elliptical, so the distance between Io and Jupiter changes up to the point where it's essentially being baked from the inside. So much energy, tidal energy, is being input into it that there's active volcanoes happening on it right now. This was an image taken from Juno, the Juno orbiter in the last decade. I actually forget the date of this one. And then on the left is infrared of some of these volcanoes. You can see the spatial distribution of them. This is still an open question in science, is how do these surface manifestations of this heat trying to make its way out of Io actually correlate with the volcanoes? Because it's not an exact one-to-one relation to the tidal potential being put into Io. This is a whole lecture in of itself. It's really neat. But just to show you the power of tides over time and how much tidal friction you can get in some of these bodies. So back to the moon. I kind of glossed over the large scale structure earlier. I mentioned it verbally, but this is a good representation of what we think is in the moon. Solid inner core, maybe. I want to argue with colleagues about the existence of it, but there's models that fit both of them. A fluid outer core, kind of like the Earth. There's this mushy partial melt layer, and then a olivine-rich mantle with a crust on the surface. We think the near side crust is a lot thinner than the far side. That's actually one active area of research I'm trying to work on, is sort of the origin of that near side far side asymmetry. But if we can think of this in terms of cheese for a moment, if we think of a partial melt layer that may be a little bit ooier and gooier, that may be a nice brie cheese, whereas the outer parts of the moon in the present day are a lot more rigid and resist deformation a lot of the time, perhaps like a Parmesan. There's sort of some recent studies based on some minute changes in the gravity field that I'll get into a little bit more in a second, published earlier this year, where they think that based on the tidal response, the near side mantle has some partial melt or some ooey gooiness comparatively to the far side that we can't really explain. And if we think back to the start of this presentation, thinking about how this mantle overturn may have occurred, maybe there was more overturn on the near side, maybe it only happened on the near side. There's still some ideas being thrown around as to if the lunar overturn even happened. But again, the near side has this nice ooey gooey-ness to it, like a brie, and the far side is a little bit more rigid. And I promised cheese geophysics a little bit earlier. This paper, or ignore that text for a second, but the really interesting thing here on the right is that Schreiber and Anderson in 1970, this is right after some lunar samples got brought back, and you can measure the density of the rock, but also how fast pressure waves go through it. So I was mentioning seismic waves earlier, and there's the P wave and the S wave. You can actually measure how fast the P wave goes through rocks, and there's some nice relationships between pressure waves and density that are pretty well described for terrestrial rocks, basalts, granites, etc. But at the same pressure velocity, sort of here, lunar rocks are a lot more dense than terrestrial ones. And I should have drawn a box around this, but if you were to inset down here, that's sort of a plot of VP and density for different cheeses. So Munster is down here, cheddar is here. Actually, let me do it with this. Yeah, Munster is here, cheddar's here, provolone, Romano, and some other cheeses that I actually don't know about. But this sort of was a conundrum in the scientific community, why these lunar rocks were a lot more dense, but had at the same like pressure velocity were a lot more dense. And it actually has to do with the bombardment history of the moon. Now, feel free to read that paragraph at some point. But essentially, the moon has been, because it doesn't have an atmosphere, you don't have plate tectonics or cycling stuff. It's just been bombarded by meteorites for 4 billion years. And I saw a talk a couple months ago that equated to the total energy spent in asteroid impacts through the entire history of the moon is equivalent to like many factors larger than the entire nuclear arsenal of the entire world. I actually need to go back and do the math myself, but someone was giving a talk and said that, and it's been sticking on my mind ever since. But that means that the upper couple kilometers of the moon are just heavily fractured. You've probably heard of like regolith before, just this like really unconsolidated material in the first few meters. Those fractures keep going essentially, and we think the first couple kilometers of it are just these large scale fractures from large impacts. But what that means is that for sort of a same measured P wave velocity, or actually at the same density, you actually get a lot lower P wave velocity because of all of that porosity. Porosity is the enemy of acoustic waves traveling through things. So it'll be the same density, but a lot lower of a seismic velocity. And there's a really snarky quote from this paper I quoted where the comparison between lunar and terrestrial rocks is thus a reminder of the danger of reaching conclusions from limited measurements, which is very nice. Dave Stevenson's a professor at Caltech for reference. So where my work comes in is I mentioned some really minute changes in the gravity field, and generally speaking, spatially across the sphere, they kind of look like this that I'm measuring. So we have measurements of how the gravity field changes degree 3, degree 2, but all it means is where latitudinally and longitudinally that gravity is changing. I threw a table of the actual measurements up here, but I realize it doesn't really matter. But essentially, because there's a difference in a lot of these wavelengths, you can actually back out what laterally variable interior structure is causing these, whether that's in terms of density, elastic properties, thermal variations, compositional variations. There's sort of like a whole suite potentially of models that can fit these data. And this is sort of some preliminary work I'm doing, and these look really boring at first. But essentially the left, I'm putting variations in this mushy layer above the core mantle boundary versus just the entire mantle. And we're currently in the stages of writing this up and trying to reinterpret what these variations actually mean. Do we actually have this mantle overturn that happened 3.8 billion years ago, and is it being preserved today? And how does that correlate with the volcanism we have seen in the past as well? Another thing we're doing is the actual time variation in those gravity fields. So the response at a year is going to be different than a day, essentially. And what that means is, depending on how the material is responding, you can get different responses depending on the model. So at a year, you could have two different responses versus a day that are going to look identical. So actually looking at the frequency dependence of that forcing is important as well. And from those, you can actually back out like the properties of the moon, essentially. So what I have on the left is just fitting some of the properties taken from variations in those gravity fields at a month and a year. And you can actually figure out, oh, it's actually a really low viscosity mantle with some certain properties about the dislocation mechanisms that are responsible in the rock. So it becomes like a rock mechanics question on how we're measuring sort of a deformation of the mantle at different wavelengths. How does that actually translate into the until what we care geologically about the interior of the moon? And with that, I think I'm right at 30 minutes. I appreciate you all listening. This was really fun. And I'm happy to take any questions.
All the way in the back. Please bellow.
With the laser range.
Yeah.
How powerful are the lasers? I assume they're Earth based.
Yeah. Oh, that's a really good question.
Kind of marksmanship does it take to get marksmanship?
Yeah. Oh, I wish I could tell you more of the details. It's a pretty powerful laser. There's a station in Nice, France that does it. There's a station in New Mexico. I think they used to do it at JPL, the Jet Propulsion Laboratory, as well. I'd have to look up numbers on the power. Enough to where, because it's going to spread over time as you're like shooting into the moon, enough to where you can still measure like a response back. But I need to look up the numbers just because I don't do laser, lunar laser ranging. I have colleagues that do, and I take their results and I do stuff with it. But yeah.
In regards to that, the Earth is much more active than the surface of the Moon is.
Mhm.
When you're doing those laser bounce backs and everything else, how do you take into account what's happening on Earth?
Yeah, there's models that predict, depending on where the laser is. We know, generally speaking, how fast some of the tectonic plates are moving, which is on the order of like millimeters a year. I think they actually move about, where is it, centimeters here? It's about as
5 centimeters.
Thank you. Yeah, because I remember the anecdote. It's about as fast as your fingernail grows.
Yeah.
Right. Yeah. So there's models that take that into account, and also atmospheric ones to account for like aberration and other things. Yeah, it's kind of black boxy to me, but I know they do their due diligence and account for a lot of the variations on Earth, because I can imagine it's pretty difficult.
The readings that you get back,
Yeah.
are they in centimeters, millimeters? I mean, how much of a
Like, what is the
variation
precision of them almost?
Well, I mean, how much does it change from 10 years ago to now if we're still?
Ooh. It's a really good question. Let me get back to you on that, because like there's variations in like the precession of the moon over time, and I'm not sure within the last decade what those precise like movements were, because essentially correcting for all like plate tectonics, atmosphere, you can measure sort of a response that's being induced by changes in the distance between the Earth and the moon, essentially, because it's in a slightly eccentric orbit. That's over a monthly period, and then over a yearly period, the same thing happens with the sun. As far as numbers go, I don't know off the top of my head.
Okay, thank you very
Yeah,
much.
yeah, thanks for having me.
Okay, I'd like to introduce Anthony Englert, who's going to speak to us about a trip to Cerro Tololo, and let us give him a warm skyscraper welcome.
So, hi everyone. My name, oh. Hey folks, I am Anthony Englert. I'm a PhD candidate at Brown University, doing my PhD in astrophysics. And I'm here to talk a little bit about a trip I was able to take to Cerro Tololo. Before digging into the details of this trip, I want to talk a little bit about just what modern astrophysics looks like. These days, from observational astrophysics, the observations that we take are very, very optimized and very, very streamlined. Many observatories these days are operating in a queue mode, where different pointings are just coming into the computer in the telescope, and the telescope then automatically knows exactly where to slew to take those observations. Kind of classical observations are becoming a little bit less common over time. We're manually telling the telescope exactly where to go. And in some cases, this is actually a really good thing. It means that we can do efficient, highly efficient operations. And at this point, around the globe, every night, we're collecting terabytes of data. That's what the average smartphone now is 100 gigabytes, right? So that's 10 smartphones. Oh, no, yeah, something like that. It's like 10 to 100 smartphones, or just filling up entire disk drives on people's laptops in a night. And this is a really good thing. It actually lets us do really unique science that we can understand, like science with a rapid cadence. From the astrophysics perspective, cadence here is just the time between the observations that you take. And so when you can image things with a really rapid cadence, it means you can pick up objects that are moving from exposure to exposure over time. Doing that more and more often is essential for capturing things like, in this case, just a little GIF of a variable star. But there are lots of other discoveries that you can make in the time domain, where things like asteroids, you have supernovae, and all sorts of other really interesting phenomena. But there is kind of a downside in that sometimes people are spending a little bit less time observing as going through academia as an astronomer. And there's an increased focus on data science, because the question is, how the heck do you process a laptop's worth of data in a reasonable volume of time? It's a hard question. In fact, much of my work is kind of working behind, this is a little screenshot of a digital sky viewer that I will just use as my sanity check for figuring out what I'm actually looking at. And it's easy to lose track of the massive teams that make observations and that make modern astrophysics possible. These are large teams of engineers and staff astronomers who support these observatories, and they have to constantly solve ongoing engineering problems. Enter Tololo. So, in support of my thesis, I was very lucky to receive travel funding to go to Cerro Tololo to carry out my observations in person. Cerro Tololo is the home of the Cerro Tololo Inter-American Observatory, or CTIO for short. It's an observatory ran by NOIRLab that hosts a wide array of telescopes dedicated to optical astronomy. It's located in Chile. It's about 3 hours, I think it was 3 hours from La Serena, roughly. It was a drive. The telescope that I was operating, which I'm showcasing here, is the Victor M. Blanco telescope, which is equipped with the dark energy camera, which is a wide field camera that was built to carry out a large survey of the southern sky. I also want to note that I got very, very lucky to get the funding in the current funding climate.
Yeah.
I think it was actually, what happened was that right when I got the approval from NOIRLab to travel was right when Brown said, we're pausing all travel funding. So I just scraped by. Traveling to Tololo is a journey of itself. It's located, as I said, a few hours outside of La Serena, Chile. It's a 12 hours of flying from Boston to La Serena, and then 3 hours of driving to actually get to CTIO. which is lots of travel. I think I was in the air for like 20 hours total, going round trip, something like that. The mountain itself is covered in all sorts of fauna and lots of little critters, and it is up, I think it was 3,000 meters above sea level, something like that. It was a couple more. It was more than that, but I digress. It's high enough to get a really great view from the dining room of the entire valley, because you're on one of the highest peaks in Chile. So there's a wide variety of telescopes that are hosted there at Cerro Tololo. At the very peak, which is this main area here, you have a wide array of telescopes, including the big one, which is the Victor and Blanco telescope, which has 2 instruments on it. The one that I was using, which is called DE cam, or the dark energy camera, which is a wide field of view optical camera. And right now it also has a near infrared camera equipped. And it is a 4-meter class instrument. So it's approximately, I think it was 3 or 4 of my cells stacked on top of each other in diameter. This is the way I like to think about it, which still doesn't do it justice compared to actually looking at the mirror. There are also 4 other smaller telescopes, smaller in quotation marks, in the astronomy telescope size sets, located on the peak. 2 of them are set aside for planetary defense. 2 of them are co-owned by the SMARTS collaboration in Georgia State University. And these are varying from 1 meter to 1.5 meters in diameter. There is a growing, what people have been calling a little mushroom farm. If I go back, you can see this little collection here at the next peak down. And that's a small collection of telescopes, which are dedicated to doing generally, observations with a fast cadence. There are a couple of other smaller, again, I'll always put quotation marks in because they're still huge, telescopes kind of popping up, slowly building over time. One of these is something called the prompt collaboration, which is really cool. It's these little shell-like, I don't know what to describe them, but the whole dome like flips open. It's really cool. You can see it happen every night. It's a set of robotically operated telescopes that are built to follow up on transients or events that happen in the time domain, i.e. someone detects something once, a quick flash, everyone tells their telescopes to point at it. I don't know why the astronomy community settled on calling them transients, but they did.
Are they remotely operated?
They are remotely operated. And one of the cool things that they actually do with these is they've turned them into a platform for community science projects. So high schoolers, I think anyone in the broader community can submit little projects to this network of telescopes. The prompt collaboration specifically, what they focus on is they focus on following up a very specific set of transients. But those transients are very rare. So they actually have a lot of downsides or downtime, which is why they open it to the community for submission, which is really great. On the neighboring mountain, Cerro Panchon, there's another collection of instruments as well, Gemini South, SOAR, and the Rubin Observatory. This is in fact a picture of Cerro Panchon from Cerro Tololo. It's right here. And if you crop into this picture that I got, you can just barely, although the screen here doesn't help, see 3 little white dots, which is the new Verisi Rubin Observatory, Gemini South, and Southern Astrophysical Research Center, which is an 8-meter, 4-meter, and 8-meter telescope, respectively. So, operations on Tololo. The entirety of Tololo is operated by a large team. There's well over 20 staff astronomers and engineers that are keeping the place ready for operations, doing maintenance, etc., 24/7. There are also a couple of telescopes, co-owned or co-operated by universities, which have graduate students maintaining and operating the telescopes on months-long runs. In fact, one of them, actually, the 2 that I met there are on an observing run again right now, and they have been on social media. They've been posting daily reviews of the of the food from the dining hall. One of them got a really great suggestion was to bring Cajun seasoning. And they've been experimenting with that. The really cool thing about this is that the day starts around 3 p.m. Typically you wake up at like 11, 12, in my case, 3 or 4, because I was sleep deprived constantly. You wake up, you go up to the peak to take calibrations, come back down, eat dinner, go back to the peak again, and start running the telescopes. And doing that every single night for some crazy number of nights. Operating a telescope like this was like unbelievable. I was like a kid in a candy store. They set you up with a really cool monitor, lots of widgets and things that you can use to monitor the seeing conditions, that you can use to monitor the weather conditions, monitor where the telescope is pointing and everything. One of the really cool things about Blanco, actually, the Victor and Blanco telescope, is that it was actually built first in 1976. One of the crazy things that the engineers do now is that the telescope was built so long ago that some of the companies that created the parts for it, they don't just not create the parts anymore. The companies don't exist anymore. So they have to go through, order custom parts, keep things operating in a completely custom way. One of the cool things, which foolishly I forgot to add the picture of it, they have the original control panel from 1976 up there in the dome, which still operates, which is absolutely absurd. A lot of Blanco in particular was actually modernized for the Dark Energy Survey, which started in 2012-ish. So there's tons of different science to carry out on Tololo, and you guys were foolish enough to let someone who studies astrophysics talk about their research. I'm not going to talk about it very much because I wanted to highlight Tololo, but I can't help myself. There's lots of interesting science you can do on Tololo. The SMARTS collaboration is dedicated to stellar astronomy. So one of the crazy things
I just send screenshots from. I'm so sorry.
No worries. One of the crazy things about the SMARTS collaboration is they've been doing an ongoing survey of Milky Way stars for the past 20-ish years, I think it is. And one of the crazy things is that their observations are so
I
streamlined.
didn't get that. Could you try?
That their graduate students are given instructions to get the star on the exact same pixels on the camera for these imaging over and over again, which is absolutely absurd. Prompt, the Las Cumbres, can't pronounce that. I can't pronounce things. It's fun. And other observatory and other projects that have telescopes there are all interested in the time domain. That means following up on transients. That could mean looking for asteroids, dozens of different things. And there's a really cool solar telescope that's located on site as well. This isn't a picture from it. I just needed a picture to put here. The research that I actually do, though, is extragalactic. So what I do is I study galaxy clusters. Galaxy clusters are massive collections of something on the order of several hundred galaxies. And when they form together into these large clumps, these large gravitationally bound clusters of galaxies, the galaxies within a cluster undergo really unique evolution driven by the environment. There's lots of gas that's thrown about. There's lots of complex feedback. Gravity is trying to pull everything together. It's a very complicated environment. The project that I was focused on was actually a galaxy supercluster, which honestly, half the reason I wanted to do this topic was because I was talking with Jan at a conference, and Jan said supercluster, and my mind just tuned everything else out. And I was like, supercluster. What could be better than that? So the Hercules supercluster is actually composed of 3 separate smaller clusters that are all really close to each other and are gravitationally bound. And the project that I was interested in, and that I'm currently processing the data for, is doing weak lensing science on the supercluster. So uses a process called gravitational lensing. Most of you, a lot of you will know, a lot of you will not know. The long story short of gravitational lensing is that matter can bend light around it, kind of acting like a lens to your glasses. And it can then lens background galaxies by taking something that's initially a circle in shape and going bloop, blooping it into a little ellipse. And in fact, when I explain that to my partner, she still will say, "Oh, how's the bloopage going?" Which is, it's literally what it is though. In fancy terms, we actually just call it the shear, but it's literally just blooping a circular object into a more elliptical shape. So what we do specifically is in weak gravitational lensing. We don't look at the regime where mass bends things a lot. We are usually looking at the regime where mass bends things very, very little. In order to pick it up, we actually have to average over lots and lots of background galaxies because each galaxy is oriented along the line of sight at a random angle. But the reward of doing that is that you can create a map of the mass across a cluster. This is currently what we're working with Hercules so far. The Hercules supercluster so far, which is very strange for multiple reasons. But for local clusters in particular, which is the stuff, I should have put local in quotation marks, local in the astrophysical sense of local galaxy clusters, it's hard to do. The signal for weak lensing is very, very weak for nearby things. It requires excellent observing conditions, a wide field of view and dark skies, which is exactly what Tololo gives us. It's why we had to do it using DECam. One of the cool things about this, just to explain this, this is optical data. Actually, this isn't my optical data. I was lazy when I put this together, and I used the online sky viewer that I showed you guys earlier. But one of the cool things you can do is you can upload other images to render over and overlay. And so what I've done here is I overlaid where we think the matter in this cluster is, or in this supercluster is, relative to kind of the optical data. So all of this yellow gold color is where we detect matter in the lensing data. But everywhere where you see galaxies is where the galaxies are. The thing that's currently puzzling me and Jan, for better or for worse, is why we see offsets between the brightest galaxies in this particular complex and a lot of the other matter. But I just wanted to talk about my research a little bit. Back to Tololo. One of the cool things about Tololo is this dark skies. Chile has strict lighting standards that help keep the skies across the country dark. This is great for health reasons, for conservationists. And the thing that we care about, I mean, everything else is great too, but the astronomy part is wonderful. There are teams, in fact, on the peak that are dedicated to tracking down and removing potential light sources. In particular, what happened one day is that when they were observing, they noticed this is a city that's about 90 minutes away that built a new stadium, and they didn't build lights tuned to the standard. So they actually had to go through all the city, all the stadium, get them in compliance, go through everything, and afterwards, huge difference in terms of light pollution. The cool thing is that the only difference between this is just kind of putting a little hat on the light so that it reflects the light downwards. One of the great things about Tololo, I managed to, earlier was a shot with my DSLR that I managed to cram in my luggage somehow. This is that city in a 10, 15-second shot. And this is without a very aggressive stretch applied. It is very minimal, especially compared to trying to do anything remotely like this for Providence, which is a nightmare. Like when I first started TA, I thought to myself, oh, it'd be so cool to see, like, because at the right time of year, you can get the Milky Way setting over part of Providence. And for some reason, my brain didn't think that's Providence. One of the amazing things about this was that the large Magellanic Cloud and the small Magellanic Cloud were both visible to the naked eye, which was crazy to see. And the thing that really blew my mind was that after staring for long enough, even the bar in the LMC was visible, this little part. And one of the cool things, so this is that's the Victor and Blanco telescope. And you can see there is a light reflecting on that. That's the moon.
Wow.
One of the crazy things about being out there was that once your eyes adjust to the darkness, the moon is like looking into a flashlight.
Yes.
Like instantly, night vision is just gone. One of the things that blew my mind, which was seeing the constellations flipped. As you travel from north to south, you yourself are going upside down on the globe. So when you look out at the sky, you see everything upside down. Which is, it's like a joke online that Australia sees the moon upside down, but they literally do relative to us. And like my favorite part of this is, for some reason, I was staring at the moon too long. And it got to the point where my mind managed to find a cat face in the moon. I don't know how, but it did. I went to Chile and I was looking at the moon and I was very confused because I couldn't find it. And now it's just gone. Like when I look at the moon, I don't see it anymore. It's crazy. Of course, one of the best parts about this was packing my DSLR in a tripod so I could take advantage of the clear skies. This is one of my favorite pictures, which is a picture of the Milky Way right from behind the dome of Blanco. And the thing was actually to get this angle was a nightmare. I had to like tilt my tripod at like a 45-degree angle. And it was at the point where I just eventually reached the point where I was like, okay, this is what I'm gonna do. And I just laid on the floor, clicking the button and then staying very still for about 30 seconds while it took pictures over and over again. And for the Milky Way over the SMARTS telescope, which is gorgeous. In fact, right after, so one of the graduate students was operating this. Right after I finished this sequence of exposures, he rotated the dome. So then I just settled for the depth that I got with this many images. And that's kind of it. I really wanted to come here and showcase what makes places like Tololo really special. Minimal light pollution is a very rare thing and becoming rarer and rarer. And you're surrounded by telescopes and all sorts of observatories and partnerships, and they're supported by an amazing team. One of the things that's sometimes hard to get, especially as we're doing a lot of remote work, remote operating a telescope, is that there's this holistic part of the experience which kind of makes it magical. Although I do have an affinity for what they call the remote operating mode in Lab. They call it pajama mode. But that's really all I had to say.
Does that like personally have any effects from the altitude? Because it sounds like we're about 9,000 or 10,000 feet.
Yeah, so actually, I didn't get altitude sickness, but what I did do is I didn't critically think, and I got really short of breath multiple times. And at one point, actually my first night there, I got lost on the peak. I went down the wrong road. And like it's one of those places where it's super hilly. So I reach a certain point where I'm just like, you know what? I'm just gonna stay on this road and hope it turns around. So I'm huffing and puffing. I have not slept for 36 hours. Because that was the first night that I got there. And fortunately, I was on the road that was a loop. But yeah, no altitude sickness for me. There is someone who is really there's someone who does work on both Panchon and Tololo, Panchon is slightly higher altitude than Tololo. And one of the funny things is this person, he gets altitude sickness at Panchon, but not at Tololo.
How many observing nights did you have and were they all clear nights?
They were all clear nights, mostly. So Tololo, it's one of the best observing spots. I forget what the statistics are for nights lost due to weather. But I think the only site that outclasses it is Mauna Kea in Hawaii. But yeah, I got all clear nights. There was one night where it was partly cloudy. And foolishly, because I was in control of the telescope, I was like, okay, I see a gap in the clouds there. I'm gonna slew the telescope. Oh, they got covered up. Oh, but there's one right there. I'm gonna slew the telescope. And the thing is that it sounds dramatic, but the telescope takes like 2 minutes to slew. So it's more like this. Oh no, there's a cloud in the way. Going back. Fingers crossed this time, and then you have to wait 5 minutes to actually see the picture that it takes, and then you have to do it all again.
With these galaxy clusters, I've seen pictures, they almost look like spider webs or like tendrils on them.
Oh, the large scale structure of the universe, yeah.
Yeah,
So-
is this your research sort of related in mapping out some of those?
It's related.
Okay.
So the large scale structure of the universe is the fact that galaxies tend to form these long filaments throughout the universe. Galaxy clusters are the knots, where many filaments tied together.
Okay, thank you very much. Well, I think you can all read pretty well. We're very excited to have Michelle join us, and let's give Michelle a very warm skyscraper welcome.
Thank you so much for inviting me. It's great to chat with a room of people who are so enthusiastic about astronomy. Of course, today is the day that my voice goes, so I'm a little bit raspy tonight. But I'm excited to talk with you about some of the most extreme types of planets that we're aware of. And one of the longest standing puzzles in the study of exoplanets, of planets around other stars, not our own star. And I say a long-standing puzzle. Exoplanets is a pretty young field. So I'll just make sure I have my controls. There we go. We'll go in the way back machine to a time when we had never detected a planet around a sun-like star besides our own. Back to 1995, way long ago. For what we knew about what planet systems can look like. Now, so here's our solar system. You always have to be careful about the scales of these things. So here, the distances roughly to scale, the planet sizes, not so much. But looking at the distances, you can see that close in to our sun, we have the terrestrial planets, these kind of rocky planets more similar to Earth. You move farther away, you have the gas giants, very big, structure completely different, quite far away. So we're expecting, when we detect an exoplanet, maybe it will fall in something of those categories, but instead we see something where this red star shows up. We see something within 1/10 of Mercury's orbit. So that's a little weird. But worse than that, we see something that looks like Jupiter mass, that close in to the host stars. So something very, very strange. Just to show this picture in a bit of a different light. Here you have a log scale plot. So you can kind of see with a log scale, the distances, the inner planets aren't so crowded in. And on the x-axis, separation from the sun, y-axis, we have the planet mass. And this is our solar system again. You see kind of bottom half of the plot, terrestrial planets and the giant planets. And this is 51 Pegasi b. So this is the first detected exoplanet around a sun-like star. And when Kellos and Mayer were first preparing to publish this work, I think they were probably pretty nervous about it. Not just because it was the first exoplanet detected around a sun-like star, but because this planet really shouldn't be there. It's a crazy thing. It's almost embarrassing to find a planet there. It goes against our very well-developed theory of how planets form, a theory that is tailored to the only case study that we have, which is, our solar system. So this is an inconceivable planet. How did this happen? No one knows. So I'll just explain for a little bit why it's such a problem to have a Jupiter-like planet so close in to the host star. Well, when we think about planet formation, our theory of planet formation, which we're pretty confident of, is that planets form in what we call a protoplanetary disk, and these disks surround young stars. These big disks of gas and dust, and these dust and gas coagulate and form planets. There's some debate over how that happens, but you think we form these kind of pebble-ice things. They accrete, they form a rocky core of a planet, and that rocky core can sweep up some gas. And we've actually kind of seen this in action a bit. So we have beautiful images of these protoplanetary disks from the ALMA telescope, have gorgeous, detailed structures. But more than that, more than just seeing structures within these disks, we actually have an example, more than one example now, where we have seen a disk that has a planet within it. So we can kind of see this happening in action. So I'll explain a little bit why is it a problem to see something like Jupiter so close into the host star, given our theory of planet formation. So there's a very important feature in the disk is the ice line. That's where things like water that are gases close in, that are volatiles or gases close in, can condense out and form solids in the disk. And the reason why that's important is because the amount of solids that you have available determines whether you're able to make a big rocky core to the planet. And you need a big rocky core and able to have a huge gas envelope. So in order to build something like a gas giant, you need a big enough rocky core, about 10 Earth masses, to start to collect a gas, and then it can become a runaway process. It goes bigger and bigger and bigger. But if you can't build that core in the first place, and if you don't have a big gas reservoir, then you shouldn't have the conditions that you need to make something like Jupiter. So here's a disk with an ice line, and you're making these kind of bigger cores over here. You can have some nice gas giants. So in our solar system, we see things like Jupiter, Saturn, Uranus, Neptune, far away, and far away from this, and then closer in, you can see the rocky planets that aren't able to get these big envelopes of gas. So as we detect more and more planets, more and more planets around other stars, we start to see more and more of these hot Jupiters. And it makes sense that if these exist, they're what we're going to see because they're easy to see, right? They're close into the host star, so they can complete an orbital period very quickly. Their year is a few days. So if you're looking for a repeat signal, that's nice. It shortens the amount of time that you have to stare at a star in order to see multiple passages of the planet. And also these Jupiter-sized planets, they're big, they're very massive, so they can create a lot of wobble in the star because of their stronger gravity, and they're very, they just take a lot of space. So if you're looking like in a transit, if you're trying to find an exoplanet by seeing that it blocks light from the star, then they're going to block more light because they're bigger. So we're seeing more and more of these hot Jupiters, these inconceivable planets. And it's starting to be a bit of a problem. So we need to develop a theory. How do these planets come to get where they are? So we need a theory of migrating planets. I should say, as an aside, there are some ideas of how you can form something like a giant planet, like actually kind of in situ, kind of close in. But the more popular theories for how we get hot Jupiters are all migration theories. They're all theories of how a planet can start at an orbit far away beyond the ice line and then move in to the orbit that we observe close to the star. And there are two main categories of theory for how that can happen. One is that the planet moves in close to the star, it moves into its present day orbit while the disk is still around. Well, you still have that big disk of dust and gas. And then the other category would be that's something that happens after the disk disperses, because the disks don't stay around forever. They stay around for maybe a few million years. And that seems like a very long time, but on the timescales we're talking about, it's not that long. So migration in the disk, this is a simulation of what a type of migration of a giant planet would look like, something very massive. And that the giant planet here can actually clear out almost like a gap in the disk. And you see that it, as it moves around in the disk, kind of launches like these spiral waves. There's a lot of cool features. But overall, the result of the planet kind of interacting with all of the stuff around it is that, if the conditions are right, will over time spiral inward. And as it happens, its orbit will shrink smaller and smaller, but it maintains a fairly circular orbit. Right? So it's kind of like a circle, it's gradually shrinking is the shape of the orbit. If the orbit becomes too eccentric, if it's too oval shaped, then interactions with the other kind of gas around will tend to kind of nudge it back onto something that's more like a circle. Another theory of how you can get hot Jupiters is that this migration happens after the disk disperses. The disk is kind of like a mediator of interactions between other planets. So in some of these systems, you can form multiple giant planets. We have multiple giant planets within our own solar system, and the disk sort of keeps everyone in line. But once the disk goes away, they can all tug at each other, and kind of mess up each other's orbits a bit. And sometimes the effect of this can be quite dramatic. If you have sort of packed in massive planets that are tugging on each other, they have strong gravitational interactions frequently, over time it adds up. And you can eject planets from the star system or launch a planet onto a very, very eccentric orbit, something that looks kind of like this. There's a lot of ways. You can pick your favorite way to get a giant planet onto a very, very eccentric orbit. And once it's on this kind of orbit, then you have very strong gravitational interaction with the star, once of this short time span per orbit. So have really strong gravitational tug from the star and go back around. This raises these really interesting tides on the planet. So one of the things that I've studied a lot is the kinds of tidal effects that you can have when you have a giant planet in a really eccentric orbit. And you can see some kind of crazy stuff happen. But overall, the net effect of having this strong tidal interaction, kind of like tides we've already heard about this evening, but in a giant planet, is that the orbit is going to circularize and it's going to shrink down into a much, much tighter orbit, into an orbit that looks like something like a hot Jupiter orbit. So this is the other picture of how you can get a hot Jupiter. This is an exciting time to study the question of how do these hot Jupiters form? How do they migrate? Because missions like TESS have full sky coverage, and it's easy to see hot Jupiters. So you can have a really unbiased sample of all of the nearby hot Jupiters. And that's something that can be hard to accomplish in astronomy, is to have a truly unbiased sample. So it's fantastic, because then if you have a large unbiased sample, you can start to dig through and try to learn things about the population. There's lots of things that you can look at about the populations of hot Jupiters. But here's a few of the more obvious ones, the low-hanging fruit. You can study the orbits of the hot Jupiters. Exactly what do they look like? How are they shaped? You can study the companion planets. Do they have any planets around? Do they have any planets in distant orbits? And do they have any planets close in? And you can study the host stars. It's sort of like, you're getting to know someone. If you want to know about them, maybe if you really want to know them, you also know, what are their siblings and their friends like, the other companion planets. You want to know about the relationship with their parents. How do they go on with the host star? So we want to figure out everything that we can about these hot Jupiters. So let's take a look first at the orbit. So this pot is filled in more now. This is from 2018. That's 7 years. Gosh, 7 years ago. So what has happened? But the message of this pot kind of stays the same. So you can ignore the colors of these diamonds and just look at where the diamonds are. Here on the x-axis, you have semi-major axis, so how far the planet is from the star. And this plot includes more than just hot Jupiter. So this line here, this is about within here. It's about where the hot Jupiters start. I'm just going to cut that off to kind of focus in. And then on the y-axis, we have eccentricity. So that's on the bottom here, you have something that's perfect circle. And way at the top of the plot, you have something that's just barely bound to the star. It'll come by once, it's not coming back again. So this is the range that we're looking at. And there's these different categories in this plot. So if something is following this pathway of starting on a highly eccentric orbit that circularizes from tides, you expect it to kind of follow a trail in this red region. You don't expect to see things in the yellow regions, because if the planet gets too close to the star at the shortest separation in its orbit, it can actually be torn apart by tidal forces. There's a bit of a sweet spot here. You don't want it to get too close and it's torn apart. So that's what these categories are here. You can see that there are planets. There's a lot of these data points around zero. There's a lot of circular hot Jupiters, which makes sense. Every time the orbits are circularizing, or maybe it's circular the whole time. And there's some eccentric ones though. It's not like they're all circular. I think maybe it's a little hard to see in this plot, but if we did like a histogram here, it'd be a big, big peak at zero. So how does this stack up against our two? We'll have a little scorecard here for our migration, forming hot Jupiters through migration in the disk versus forming after the disk disperses. So there's kind of a pileup around having a 3-day year or a 3-day orbital period for these planets. They're all close in. And both disk migration and post-disk migration can explain that. They can explain that you tend to supply these giant planets at about the right separation. Another thing is that you see planets in circular orbits, and both of these mechanisms can explain that. They can produce a circular hot Jupiter. On this post-disk migration, maybe it's a little harder to make sure that the orbit circularizes within the lifetime of the star, but still, both of these theories, they can do that. The one that's a little bit trickier is for disk migration to explain these hot Jupiters that still have some moderate eccentricity to their orbit, where it's really not circular. That's a little bit trickier because for disk migration, everything should stay about circular. You can kind of like tweak your model a bit, sort of try to finesse things to make it work, but really it's hard for this theory to explain any hot Jupiters that have some eccentricity. But for the post-disk migration, that all is part of the story, right? You excite a planet onto a really eccentric orbit and then it circularizes over time. The other thing we can look at, now we'll look at the friends and siblings of the planet. We'll look at the close by planet companions. And you can also look at the distant companions, but it's limited time. We'll look at the close by companions. And here again, I'll do a little dividing line. So to the left of this line that will momentarily appear, we have the hot Jupiters. And this on the y-axis is showing a probability that it has a nearby companion. So it's a probability because these aren't necessarily detected companions. This is sort of a statistical analysis where you look for variations in the timing of transits of hot Jupiters. So if the timing of a transit's really consistent, then your very predictable orbital period for the hot Jupiter, you can predict exactly when it's going to pass in front of between you and the star again. But if there are other planets around, they can kind of tug on the planet a bit, mess that up. So you can have these transit timing variations. And that's the technique that's used to make a plot like this. But the point here is that you can see that there are some hot Jupiter companions. There are systems that we know where the hot Jupiters have their other giant planets or planets like Neptune's are close in. But a lot of them don't have companions, especially when you compare them to Jupiter's gas giants that are just a little farther away from their star. There's a difference when you look to the right of this line and to the left. So how does that stack up against our two competing, not really competing, our two different theories? So for disk migration, you would expect that everything can kind of migrate together tidally. It's very quiet and calm, relatively speaking. So if a planet has companions, it can keep those companions. It's fine. So you would expect to see some hot Jupiters with close companions. That all checks out. High eccentricity migration is kind of a different story. These planets are like a bowling ball in their star systems. So it's really hard to explain any companion planets through high eccentricity migration. So this one, a little harder to see how they fare up. So the fact that not many of these hot Jupiters have companions, it's kind of in line with high eccentricity migration, but the ones that do, that means they probably did not form that way. And the last thing we can look at we can look at the host stars. There's lots of things you can do by looking at the host stars, especially now that we're getting this lot more detections of hot Jupiters and this kind of unified sample. You can slice and dice the population by looking at like the mass or the age, whatever property you prefer of the host star. But the one that I have worked on a bit, so it's the one that I'll talk about, is looking at how the spin of the star, because the stars are rotating, how that lines up with the orbit of the hot Jupiter. So in our solar system, the planets that are orbiting are roughly aligned. It's all roughly in a plane. So it's, roughly the angular momentum of these orbits are roughly aligned with the spin of our sun. But in other star systems, it's not necessarily the case. So if you look at this angle, the angle between where the stellar spin axis points, the axis that the star spins around, and the angle between the orbital angular momentum of the planet's orbit, so just kind of a line that's perpendicular to the planet's orbit, you can measure what that angle is through a really cool technique called the Rossiter-McLaughlin effect, which I won't take time to explain. It's a very cool type of observation. And you can get a sense for what that alignment angle is. And here it's plotted for reasons I won't get into as a function of the temperature of the star. For these colder stars, you expect the star, tides within the star to quench stellar misalignment. So it's not surprising that when you look at hot Jupiters, everything around a cold star is saying that the stellar spin and the orbit are pretty much aligned. But for these hot stars, you can see some huge misalignments. It's definitely not the story that everything is lined up like in the solar system. So how does that stack up against these two theories? Well, if you have a disk, the disk migration, then everything should be staying within the plane of the disk. So if you want to tilt the orbits relative to the star spin, you have to tilt the disk relative to the star spin. Is really what you have to do. And it turns out that for something like a hot Jupiter, this is kind of tricky to do. It's you can maybe make it work, but it's challenging to have something that's really, really misaligned. But for post-disk migration or high eccentricity migration, that's a pretty easy thing to do. I talked about how you can excite the planet onto a very eccentric orbit that doesn't look at all like a circle. But what I also didn't mention, because it's kind of hard to show against the plane, is that you can tilt the orbit quite a lot. Is another way you can kind of disrupt the orbits of these systems. This seeing systems with a really high misalignment between the stellar spin and the orbit is indicating, or it is kind of in favor that some of these planets, maybe many of them, formed through this post-disk migration or high eccentricity migration. So we can do a final tally before we look kind of ahead to the future of how things are going. So I would say that it seems that planet migration after the disk disperses, or high eccentricity migration, it explains a lot of features of the observed hot Jupiter population. It's a pretty successful theory for how these form. However, there are some of these planets that have known companions, and those at least likely migrated within a disk. So it's not necessarily all one or the other. A few things are happening at the same time. So what's next? What else can we look at with hot Jupiters? So one thing we're looking at currently is not my area of expertise, but it's very cool science. It's probably the atmospheres of hot Jupiters, is especially enticing now with JWST. So we're detecting all kinds of cool features, like water features, checking molecules that we haven't seen before in hot Jupiter atmospheres. Now we can take really detailed spectra of these atmospheres. And one thing that you could think about doing, but it's hard to do, but might be possible now that we're getting in high quality data, is maybe try to connect features of different types of particles in the atmosphere to one of these migration histories. If you are migrating within a disk, you interact with a disk, pick up some disk material, maybe that looks different from what happens when you have this high eccentricity migration. And as there's tides raised on the planet, we usually about tides on Earth, right? That involves a lot of water sloshing around. Tides on a giant planet involves a lot of convection and a lot of kind of things turning around within the planet. So maybe those two mechanisms look a bit different in terms of the composition of the atmosphere. I don't know, I think that'd be hard to connect, one way or the other, but that's one avenue that you can look forward now that we have high quality data coming in. Another thing that I think is really exciting is kind of the next big thing from NASA. So Nancy Grace Roman Space Telescope is set to launch in 2026 or 2027, soon, set to launch in the next few years. And this will be able to scour the galactic core for hot Jupiters. That's really, it's not the main science purpose of this telescope. It's going to do very cool things for studying dark matter, that kind of stuff. But one cool bonus for exoplanets, so you might be able to see hot Jupiters within the galactic core, which is a really different environment from where we've looked for hot Jupiters so far. A lot of the hot Jupiters we've seen are around young stars. So do we see hot Jupiters that look the same around older stars is an interesting question. And things that are in the galactic core, stars in the galactic core, it's a denser population with more stars there. So you can kind of, one star can pass closer to another star. Like, does this affect the history of, or how does this affect planet formation is a very open question. So lots of cool things that we can do looking ahead to the future with James Webb and in a few years with a Roman Space Telescope. So thanks for your attention.
Questions? Yes,
You just mentioned all stars. Have there been any hot Jupiters discovered in globular clusters?
I don't think so. Yeah, so far I would have to check to be sure, but I don't think so. Mostly been looking at things. Most of the Jupiters that are seen are like around kind of younger stars. We're looking at sort of bright stars in our nearest by. Yeah, to check.
I got a twofold question. What types of stars, young or old, have we found hot Jupiters?
Yeah, so that's a really interesting question. It seems like, and this is kind of a recent result, I think, it seems like hot Jupiters are most likely to form around sun-like stars.
Okay,
So as you go down,
type stars.
yeah, exactly. As you go down to like M dwarfs, like not so many hot Jupiters. And as you go higher mass, I think also not so many hot Jupiters. It seems like maybe it peaks around sun-like stars.
My second question was, have we found any evidence of, if we look at the older G-type stars, of any type of exoplanet activity? And I'm talking something similar to our own solar system. Is there any evidence there's anything like that out there?
Have we seen anything like our solar system? Our solar system is pretty unique. I don't think we've seen anything that's like a direct solar system analog so far. It turns out that our, if we're talking a lot about how these giant planets move in other star systems, but our own planets close by have also probably moved around quite a bit to reach the configuration we're in today. Yeah, it seems like we're, I don't know of anything that's like very, very close to our solar system.
Thanks for the great presentation. My question is, do we know whether or not a hot Jupiter orbit is stable in the long term, or is just a transitional state to being destroyed by the star?
Yeah, that's a great question. So I presented it as though you reach, circular orbit and like you're done, you're set. Well, that's not really true. There's also tides in the star that over time are acting to shrink the hot Jupiter orbit. That's another question when you look about like trying to parse out, do we see hot Jupiters around older or younger stars? Like, are the older stars like gobbling up all of their hot Jupiters? Is a very interesting question to raise. Also, there are hot Jupiters that we've seen where we can detect decay in the orbit, and I think there's a growing body of them. There's one that's looking pretty convincing now, and a few other kind of candidates. It's a hard thing to observe because the time scale for it is pretty long, but that is something we've seen.
Why doesn't the stellar wind, similar to the solar wind, but why doesn't the stellar wind just break off the atmosphere and turn these into smaller planets?
So the atmospheres of hot Jupiters are pretty extreme places. So they're quite puffy, but they are kind of safe enough from being kind of blasted by something like a stellar wind. Some of them, what might happen kind of on the way to forming a hot Jupiter, if they form through this high eccentricity orbit and the circularizes due to tides, then there's a point in the orbit where the planet can come really close to tidal disruption, actually. So what might happen is not so much kind of interaction with the stellar wind, but even just the gravity on the star can kind of pull on the giant planet. And maybe that's a common thing to pull off a little bit of mass from the Jupiter on its path to becoming a hot Jupiter. That's something that I'm interested in. I don't think there's a decisive answer on that. It's interesting to investigate.
Thank you very much. That was excellent.